Okay, so let's continue our discussion. So again, lesson 6, radicals. So here we need to extend our knowledge about the laws of exponent. Let's see, raised to n. Okay, so discuss about radicals in this form, the nth root of a. Okay, so here we have our questions. What is a radical expression? How to illustrate its laws, and how to convert power with rational exponents to radical form. Okay, so here, first we need to familiarize also ourselves when it comes to the parts, okay, of the radicals. Okay, so let's start first with n. Okay, so n here is called as the order or the index. Okay, it determines what is the principal root the radicand is under. Okay, and a is called as the radicand. Okay, it's expression inside the radical symbol. Okay. So what about the radicals or the fractional exponents? Okay, so let's have the formal definition of this. So when we discuss about the fractional exponents, we have here if m over n is a rational number and a is a positive integer, then we have this a raised to m over n. Okay, so it is equal to the nth root, okay, nth root of a raised to m. Okay, which is the same as the quantity of nth root of a. Okay, so let's have an illustration here. So let's say we have here the square root of 9. Okay, so we have your square root of 9. So first we need to simplify or express our radicand in exponential form. So 9 can be expressed as 3 times 3 or simply 3 squared. Okay, so as you can see here, uh, that the radical here, we can convert it into fractional exponent. So as you observe here, our exponent inside the radicand is 2, and our index here is 2. Okay, which is our exponent denominator. So that's 3 raised to 2 over 2, or simply 3 raised to 1, that's 3. Okay, so as you can see here, when we are solving for the root, we are after with the positive value. Okay, but also we need to consider that there are times that we our answer is negative. Okay, but in this case, in square root of 9, our answer is 3. Okay, so another example, we have here the cube root of 8. Okay, so here in cube root of 8, it can be expressed as cube root of 2 cube. Okay, so as you can see here again, we have 2 cube, the exponent of the radicand is 3, and our index or our order here is 3, which is our denominator. So simplifying that, that is 2 raised to 1, which is 2. Another example, the fourth root of x raised to 4. So again, as you can see here, we have the exponent 4 over the index 4. So the fourth root of x raised to 4 is simply x. Another example, so as you can see here, we have the cube root of negative 8. Okay, so negative 8 can be expressed as negative 2 times negative 2 times negative 2, or simply negative 2 cube. Again, so as we apply the rule in the radicals based on its definition, so we have here the quantity of negative to 3 over 3. Okay, or simply negative 2. Then another example, so as you can see here, it is expressed in fractional exponent, negative 64 raised to 2/3. Okay, or simply the cube root of negative 64 raised to 2. And negative 64 can be expressed as negative 4 times negative 4 times negative 4, or negative 4 cubed. Okay, so as you can see, we have the exponent of the radicand, which is 3, and our index or the order is 3. So 3 over 3, that's 1. So that's negative 4. And then squared, negative 4 squared is 16. Another example, the cube root of 8 b raised to 6. So again, let's simplify the radicand here. So 8b raised to 6 can be expressed as the quantity of 2b squared cube. Okay, so applying again the definition, the rule. So as you can see here, we have 2b squared. Okay, another example. So let's say we have here the seventh root. Okay, the seventh root of negative 128, a raised to 14, b raised to 21, c raised to 28. Okay, so as you can see here, we can apply. Okay, we can apply the fractional exponent to simplify this. Okay, so we have here the seventh root, or simply our exponent is 1 over 7. Okay. And then we have here negative 128. Okay. It can be expressed as negative 2 raised to 7. Okay. So now, as you can see here, we can simplify this. We can use the reverse power to a product. Okay. Which is this one. The quantity of negative 2 raised to 1 a squared b cubed c raised to 4 raised to 7. Okay, so we use again the reverse power to a product. Okay, and then simplifying this, we have 7 times 1 over 7. Okay, is just simply 1. Okay, so the seventh root of negative 128 a raised to 14 b raised to 21 c raised to 28 is negative 2a squared b cubed c raised to 4. Okay, so again, as you can see, we just apply the definition and also the laws of exponents that we discussed uh, in our previous discussions. And then another one, the eighth root of 256 x raised to 16 y raised to 32 z raised to 40. Okay, so same procedure, fractional exponent. So 256 can be expressed as 2 raised to 8. And then again, eighth root, so that's 1 over 8 as our exponent. And then again, reverse power to a product here. So 2 raised to 1, x squared, y raised to 4, z raised to 5. And then quantity, and that's raised to 8 raised to 1 over 8. And 8 times 1 over 8 is just simply 1. Therefore, the eighth root of 256 x raised to 16, y raised to 32, z raised to 40 is 2x squared, y raised to 4, z raised to 5. Now, let's discuss the laws. Okay, the laws of radicals. So first off here, we use it previously in our illustration, in our definition of the radicals. So as you can see here, we have the quantity of the nth root of a raised to n is simply a. Okay, so as you can see here, if you have the exponent and your index as equal, therefore you have the answer, which is your radicand. Okay, so let's have an illustration. So negative square root of 16. Okay, square root of 16, 16 can be expressed as 4 squared. Okay, so as you can see here, we have the index of 2, we have the exponent of 2, so simplifying that, that's negative 4. Another example, the fifth root of 7 raised to 5. So same exponent and then the index, so the answer is 7, the radicand. Okay, the fourth root of AB raised to 4. So again, they are equal. So that's AB. The cube root, okay, of negative 64. So applying again, simplifying negative 64 can be expressed as negative 4 cube, quantity negative 4 cube. So again, same index, same exponent. So that's negative 4. And then last example, the seventh root of negative 1. Okay, so we can raise negative 1 by 7 and the answer still is negative 1. So the seventh root of negative 1 raised to 7, that's negative 1. Okay. Another example here is the nth root of AB is equal to the nth root of A times nth root of B. Okay, so let's have an illustration. Okay, so first off, we have your square root of 18. Okay, so let's identify the factors that we can use when it comes to 18, our radicand. So it can be expressed as 9 times 2. Okay, so square root of 9 times 2. So applying the law, we can have here square root of 9 times square root of 2. So simplifying that, that's square root of 9 is 3. And then we have here square root of 2. Okay, so square root of 18 is equal to 3 square root of 2. Another example, square root of 147. Again, the factors of 147, which is 49 times 3. The square root of 49 is 7. So that's 7 square root of 3. Another example here, we have the cube root of 16. Okay, the cube root of 16. 16 can be expressed as 8 times 2. Okay, so again, applying the law, cube root of 8 times cube root of 2. And the cube root of 8 is just simply 2. So the cube root of 16 is equal to 2 cube root of 2. Another example, the seventh root of x raised to 9. Okay, so x raised to 9 can be expressed as x raised to 7 times x squared. Okay, so again, apply the law of radical here. We have the seventh root of x raised to 7 is just simply x. And then we have here the seventh root of x squared. So we have here the answer, x times the seventh root of x squared. Example 5, the cube root of negative 16. Okay, again, we have here cube root of negative 8 times the cube root of 2. And the cube root of negative 8 is negative 2. So we have here negative 2 cube root of 2. And then number 6, last one, the sixth root of a raised to 23 b raised to 10. Okay, so as you can see here, a raised to 23 can be expressed as a raised to 18 times a raised to 5. B raised to 10 can be expressed as b raised to 6 times b raised to 4. Okay, or simply we have here a raised to 18, b raised to 6. And if we identify the sixth root of that, we have here a raised to 3b. Okay, so all you need to do is to divide it, the exponents, so to the index. So that's 18 divided by 6, which is 3. And then 6 divided by 6, that's 1. So we have here a cube b. And then we have the sixth root of a raised to 5, b raised to 4. So the sixth root of a raised to 23, b raised to 10 is equal to a cube b, sixth root of a raised to 5, b raised to 4. And then we have here the third law, and the third law of radicals, which is the nth root of a over v is equal to the nth root of a over the nth root of b. Okay, so applying this with our examples here. So number 1, we have the fifth root of negative 2 over 32. Okay, so the fifth root of negative 2 over 32. So that's fifth root of 2 over the fifth root of negative 32. So as you can see here, we have the fifth root of 2 over negative 2, because the fifth root of negative 32 is negative 2. So simplifying that, we have here negative fifth root of 2 over 2. Another example, the cube root. The cube root of negative 64 over x raised to 6. So we have here the cube root of negative 64 all over cube root of x raised to 6. Okay, and negative 64 again can be expressed as negative 4 cube. So simplifying this, let's apply the first law, having the exponent of the radicand and the index being equal. So we have here negative 4 over x squared. Okay, so the cube root of negative 64 over x raised to 6 is negative 4 over x squared. So we have here the three laws. The last law here is the m root of n root of a. Okay, is can be expressed as m times n root of a. Okay, let's have an example. Number 1. So let's have here the sixth root of 4. Okay, sixth root of 4. So as you can see here, we can divide the root or the index here. Okay, so we have here the cube root and the square root. Okay, so that's 3 times 2, that's 6. So we have here cube root of the square root of 4. And the square root of 4 is 2. Therefore, we have cube root of 2. Another example, the eighth root of x squared. Okay, it can be expressed as the fourth root of the square root of x squared. So 4 times 2, the index, that's 8. So the square root of x squared is simply x. So therefore, we have here the fourth root of x. And then for number 3, the eighth root of 16. The eighth root of 16, we have here the square root of the fourth root of 16. Okay, so we have here the fourth root of 16, that's 2. So that's square root of 2. Okay, and then another example, last example here, the 10th root of 32 x raised to 5. Okay, so we have here the square root of the fifth root of 32 x raised to 5. So as you can see here, simplifying 32, we can express that as 2 raised to 5, x raised to 5. So again, we have the index and our exponent being equal. So that's 2x. So we have the square root of 2x. Okay. Now, how to simplify? Okay, how to simplify the the radicals. Okay, so we have here actually 3 ways to simplify the radicals. So let's start first with this one. Removing perfect nth root. Okay, so break down the radical into perfect and non-perfect nth root, nth powers, and apply the property. Uh, we have the nth root of AB is equal to the nth root of A times nth root of B. Okay, so now let's have an illustration. So let's say we have here the cube root of 32x raised to 4y raised to 32. Okay, so let's apply the property. So we have here the cube root of uh, 8x cubed y raised to 30 times 4xy squared. So we divide it so we can identify perfect root to extract. Okay, so as you can see here, we have the cube root of 8, that's 2. The cube root of x cubed, that's x. And then the cube root of y raised to 30, that's y raised to 10. Okay, so simplifying that, we'll obtain 2x y raised to 10 times the cube root of 4xy squared. Okay. Other example, the fifth root. Okay, the fifth root of negative 64 x raised to 14 b raised to 128. Okay, so simplifying this again, we need to divide it to, let's identify the perfect root. Let's identify the perfect root here. So negative 64 can be expressed as negative 32 times 2. X raised to 14 can be expressed as x raised to 10 times x raised to 4. B raised to 128 can be expressed as b raised to 125 times b cubed. Okay, so as you can see here, negative 32, we can express that as negative 2 raised to 5. And then here we can extract, we can have the fifth root of that. Okay, which is negative 2x squared b raised to 25. So again, all you need to do is to divide it. Negative 2 raised to 5, 5 divided by 5, that's 1. X raised to 10, so 10 divided by 5, that's x squared. 125 divided by 5, that's 25. And then multiply the remaining fifth root here of 2x raised to 4b cubed. And then another example, the square root of 72 x raised to 4 y raised to 7 z. So again, let's identify the perfect root here. So that's 36 times 2 x raised to 4 times itself. That's x raised to 4. Then y raised to 6 times y. And then we have here the z. Okay, so simplifying that, square root of 36, that's 6. X raised to 4, that's x squared. Y raised to 6, that's y cubed. Times a square root of 2yz. So we have here the square root of 72 x raised to 4 y raised to 7z. That's 6x squared y cubed. Square root of 2yz. Other way to simplify the radicals, we need to reduce. Okay, we need to reduce the index to the lowest possible order. Okay, so reducing the index is done by applying this property, the law of radical. Here we have the m root of the nth root of a. Okay, which is m times n root of a, or expressing the radical into its exponential form. Okay, so we can use the exponential form to simplify it. Okay, so let's have an illustration. Okay, so let's have the fourth root of 4 can be expressed as the square root of the square root of 4. Okay, the square root of 4 is simply 2, so that's square root of 2. Another example is the eighth root of x raised to 6. So let's apply the fractional exponent. Okay, the exponential form. So as you can see here, we have x raised to 6 over 8. Okay, so we have the common factor here of 2. So simplifying that, that's 3/4. Okay, so x raised to 3/4, or simply the fourth root of x cubed. Okay, so either of the two, you can use that to simplify. Okay, depending on the given example. Let's have example number 3. Okay, in example number 3, we have here the 20th root of 32x raised to 15. Okay, so as you can see here, we can apply again the exponential form, the fractional exponent, that's 32 x raised to 15, 1 over 20. Okay, and 32 is 2 raised to 5, and then we have your x raised to 15. Again, simplifying this, that's 5 over 20. So uh, that's 1/4. Okay, so as you can see here, we have here the fourth root. Okay, the fourth root of 2x cubed. Okay, so again, we apply here the reverse power to a product. Okay, the reverse power to a product. Okay. Another example, the eighth root of 81x squared y raised to 4 z raised to 6. Okay, so again, the fractional exponent here, eighth root can be expressed as raised to 1 over 8. And again, a reverse process of the power to a product. So that's quantity 3 squared xy squared z cubed squared times 1 raised to 1 over 8. Okay, 2 raised to 1 over 8, or 2 times 1 over 8 is simply 1/4. So we have here the fourth root of 3 squared, which is 9, xy squared z cubed. And therefore, the eighth root of 81x squared y raised to 4 z raised to 6 is simply equal to the fourth root of 9xy squared z cubed. Okay, so as you can see here, we apply the previous law, or we can use the fractional exponent. Okay, then let's apply the reverse power to a product. Okay, and then lastly, we have here rationalizing the denominator of the radicand. Okay, so as you can see here, uh, in rationalizing the denominator of radicand, it's the process to remove the radical sign in the denominator. Okay, so our goal here is to have a perfect root, okay, in the denominator by multiplying an appropriate expressions. Okay, so always remember again, the denominator should be a perfect root, or there is no radical in the denominator. Okay, so we can use the identity property of multiplication so that we can preserve the equation. And also it does not change, okay, the value of the given expression. For instance, yeah, number 1, let's simplify the square root of x over y. So as you can see here, again, we have radical in our denominator. So let's try to think of a certain expression that we need to multiply both the numerator and the denominator so that our denominator can be a perfect root and free from irradicals. Okay, so here in this case, since we have the square root, we should have y squared, right, in the denominator. Okay, so as you can see here, we can multiply it by y, both the numerator and the denominator. So as you can see here, y over y is just simply 1. Okay, it's just simply 1. Okay, but we need to use this so that we can simplify and have perfect root in our denominator. So as you can see here, we have x over y times y over y. So that's simply xy over y squared. Okay, so as you can see here, the square root of y squared is just y, right? So as you can see, it's free from radicals. So we have the perfect root for our denominator. So square root of x over y is simply the square root of xy over y. Okay? Another example, the cube root. Okay, the cube root of 1 over 3x squared y. So again, we need to think of an expression that will make our denominator as a perfect root. Okay, so try to think. Okay, so here in this case, we have 3. Okay, so to have the cube root of this, we need to multiply 3 squared, right? We need to multiply 3 squared. And then since we have here x squared as available here, we need to multiply another x, okay, to have an x cube. And then y here, we need to multiply y squared. Okay, so here we need to multiply in the numerator and denominator 3 squared xy squared. Okay, so again, 3 times 3 squared is simply 3 cube. X squared times x is simply x cube. And then y times y squared is y cube. Okay, so applying again here the rules of radicals, our exponent is perfect root. Our denominator rather is perfect root. So simplify that. We have here the cube root of 9xy squared over 3xy. Okay. Another example, the eighth root of 1 over 64x raised to 9, y raised to 10, z raised to 36. Okay, so try to think of uh, an expression so that our denominator is a perfect root and free from radicals. Okay, so as you can see here, we can multiply 2 raised to 2, and then x raised to 7, y raised to 6, z raised to 4. Okay, so we need to multiply again 2 raised to 2, x raised to 7, y raised to 6, z raised to 4. So as you can see here, 64 is the same as 2 raised to 6. But we need again 8 root, right? So we multiply it by 2 squared. And then x raised to 9, that's we need 7. Okay, for x raised to 7. And then y raised to 10, we need 6. And then z raised to 36, we need 4. So simplifying that, we have here 2 raised to 8, x raised to 16, y raised to 16, z raised to 40 for our denominator. Okay? So simplifying that, again, applying the rule. So we have here 2x squared, y squared, z raised to 5 for our denominator. Okay, and our numerator here is the 8th root of 4, x raised to 7, y raised to 6, z raised to 4. Okay, so to simplify again, for the 8th root of 1 over 64, x raised to 9, y raised to 10, z raised to 36, we need to think of an expression that we need to multiply both the numerator and denominator. Okay, to have our denominator as perfect root and free from radicals. Okay. Example number 4. Okay, sometimes it's beyond or it's not just one term to consider. For instance, the square root of 1 over x minus y. Okay, so let's try to think. okay, of the an expression that we need to multiply here so that we can have a perfect root for our denominator. So as you can see here, x minus y, we need to treat that as one unit, okay, as one term. So we need to multiply both the numerator and denominator by x minus y. Okay, we cannot multiply that for just x or just for y because we cannot eliminate the radical in the denominator. Okay, so simplifying this, multiplying x minus y over x minus y. So that's x minus y over x minus y squared. Okay, so the square root of x minus y squared is just simply x minus y, right? So to simplify that, again, try to think of an expression. Okay, here in this case, we have x minus y. So the square root of x minus y over x minus y. Then fifth example, the cube root of 2 over a quantity a plus b squared times the quantity of a minus b. Okay, so in this case, try to think of an expression that we need to multiply on both the numerator and the denominator. Okay, here in this case, we need to multiply a plus b times the quantity of a minus b squared. Okay, now, simplifying that, we have here the quantity of the cube root of 2 times the quantity of a plus b times the quantity of a minus b squared over quantity a plus b cube, quantity a minus b cube. So as you can see here, we have the perfect root, okay, for the denominator. Okay, so simplifying that, we have the cube root of 2 times the quantity of a plus b times the quantity of a minus b squared all over a plus b times the quantity of a minus b. Okay, so sometimes it's more than just one term. Okay, but we treat that as one unit to multiply on both the numerator and the denominator. Okay, so aside from this, actually, we can use the special products in rationalizing. Okay, so for instance, we have the difference of two squares and the sum and difference of two cubes. Okay, it's very crucial for us to utilize this in rationalizing the given expressions. For instance, number 6, 1 over the square root of x plus 1. Okay, so as you can see here, if we multiply both the on the numerator and denominator, square root of x plus 1, we cannot uh, eliminate the radical in the middle term, right? We can eliminate in the first term square root of x times square root of x, but we have the middle term as square root of x plus square root of x. So we can't use that. Okay, we can't use that square root of x plus 1. But applying the difference of two squares here, we can eliminate the middle term, right? And then our first term here, we can eliminate the radical. Okay, so here in this case, we multiply the numerator and denominator by square root of x minus 1. Okay, because square root of x times square root of x, that's x, right? And then 1 times negative 1, that's negative 1. And then we don't have the middle term. The middle term will be eliminated. So square root of x minus 1 all over the quantity of square root of x plus 1 times the quantity of square root of x minus 1. Or simply x minus 1. So therefore, as we simplify 1 over the square root of x plus 1, it's just square root of x minus 1 over x minus 1. Okay, so be careful. Sometimes we need to use some special products, okay, to rationalize the given expression. Another one, x over the square root of x minus y. Okay, so again, if we use square root of x minus square root of y here, we cannot eliminate the radicals in the middle term. So let's apply again the difference of two squares. So square root of x plus square root of y. So simplifying that, we'll have x times the quantity of the square root of x plus the square root of y all over. And we have here the difference of two squares, right? So we can eliminate the radicals here. Square root of x minus y is square root of y times the quantity of square root of x plus square root of y is just simply x minus y, x plus y, x minus y rather. Okay, so x times the quantity of the square root of x plus the square root of y all over x minus y. Okay, and then another example here, last one, 1 all over cube root of x plus 1. So as you can see here, we cannot use again the cube root of x plus 1, and at the same time we cannot use the cube root of x minus 1, right? So here in this case, let's apply the sum of two cubes. Okay, let's apply the sum of two cubes. So let's multiply the cube root of x squared minus the cube root of x plus 1. Okay, so again, be familiar with the form. Okay, be familiar with the form of the sum and difference of two cubes. Okay, so that we can use that for our in rationalizing our expression. Okay, in multiplying on both the numerator and the denominator. Okay, so simplifying this, we have in the numerator the cube root of x squared minus the cube root of x plus 1. And as you observe here in the denominator, it's just the sum of two cubes. Right? It's just the sum of two cubes. So it's simply x plus 1. Okay, so in simplifying, 1 over the cube root of x plus 1, it is equal to the cube root of x squared minus the cube root of x plus 1 all over x plus 1. Okay, so remember again, be careful on what expression will you multiply on both the numerator and the denominator. Make sure you eliminate the radicals in your denominator and also you have the perfect root. Okay, and then for the last discussion, we'll discuss about the operations on radical expressions.